Okay, so when I'm teaching you something new, okay, you'll see in your notes package something that looks similar to this. There'll be a lesson number, a lesson title, okay, and some key points. All right, so today we're looking at position, displacement, velocity, okay, basically V equals d over t from Science 10. Okay, the key points would be that we have to understand that the motion of objects and systems can be described in terms of displacement, time, and velocity. Okay, we need to remember and review that scalar and vector quantities are slightly different and look at things from different points of view. Okay, and we need to obviously define velocity as a change in position during a time interval. In other words, be able to use that formula, which can also be written this way. Okay, displacement is final position minus initial position divided by time. Okay, so that's the formula we're kind of focusing on, along with a review of scalar versus vector quantities. Okay, so in this first sentence here, we have displacement, time, and velocity. Which of those is scalar? Time. Okay, time is scalar. Okay, as far as we know and are able to prove, time only goes forward. Okay? We don't know if time can go sideways or backwards. We simply can't make it flow any way other than it naturally flows. Okay? We might have, time might be relative. Okay? That's Einstein's whole theory of relativity thing. Okay? Time could be relative, but it still only flows in one direction. Our perception of it might change. Okay? But it can only flow in one direction. As a result, it's scalar. Whereas displacement is a vector quantity, and so is velocity. Okay? All right. Now, in North American society, we have this problem. We think of things the wrong way. Well, from a physics perspective, we think of it the wrong way. Okay? So, for example, if I was to ask you how far it is to Lethbridge, what are most of you thinking right now? A couple hours? Okay, one or two people will say how many kilometers it is, but most of us naturally think how long it will take to get there. Okay? You don't have to admit that's what you're thinking. That's how we generally think. Okay? The problem is that I didn't ask how long it would take. I asked how far is it to Lethbridge. Okay? How far it is to Lethbridge doesn't change. Okay? Lethbridge is X many kilometers from here. But how long it takes to get there does change. It's dependent on other things. Okay? But a problem that we have in North America is we always tell people how long it takes to get somewhere as opposed to how far it is. Okay? It's just the way we're wired. Okay? The problem is that that's not always true. Okay? You can go to Lethbridge in an hour and 40 minutes, or it can take you 4 hours, or if you walk, it could take you several days, or if you flew, it could take you 25 minutes. Okay? It all depends on how fast you're able to go. So how long it takes to get there is not a constant number. It's affected by other things. Okay? So we have to make sure that we are understanding what a question is asking for, okay, when we read it, because that's a common mistake that I see. A question will say, how far is it during this trip? And people will tell me the time. Okay? That's not what the question's asking. It's asking how far. It wants a number in meters or kilometers, okay, not a time in seconds or hours. Okay, those are two different things. Okay, so that's our problem with kind of North American societies. We just describe things the wrong way. And from time to time, that can burn you pretty bad. Okay, I had an example of this a number of years ago, backpacking with a friend of mine in the summer. And we've been hiking all day. We hiked from like 7 in the morning, it was like 5 o'clock in the afternoon. We were out of water, hungry, okay, and we weren't at the campground we were supposed to be at yet. And we didn't see any evidence of it, and we're like, we might be lost or something, or we can't be lost because we stayed on the trail. Where the hell is this campground? Okay? And so we kind of sat down to kind of collect ourselves and think, and this guy comes like jogging / running up the trail. He's wearing like army fatigues. He's carrying a pack that's twice as heavy as mine. Mine was 50 pounds. Okay? The thing was gigantic. And he's running uphill towards us. And we're like, oh, sweet, this guy will know. We'll just ask him. Like, dude, how far is it to Tumbling Creek Campground? Oh, 20 minutes. That way down the trail. Sweet, 20 minutes. 40 minutes later, we are singing the 4-letter serenade about this guy in his 20 minutes. Okay? Because it was over an hour before we got there. Okay? And then we sat down, had something to drink, had something to eat, so we were less hangry. Okay? And then it occurred to us, because we both teach physics. Man, are we ever stupid. We let that guy tell us how long it took him, as probably a Navy SEAL out for a jog carrying his heavy pack, how long it took him to get from the campground to us. Of course, it only took him 20 minutes. We're 2 out-of-state teachers on our summer vacation, and this guy's out for a jog carrying a 100-pound pack. Yeah, okay, it was dumb. Okay, well, we didn't think of it, because how do we as North Americans think? How long did it take? Yeah, it took you 20 minutes, because you were running. We weren't. Okay? So, we have to be careful about that. Now, there are times where scalar and vector can also kind of mess us up. There's times when scalar descriptions of something is appropriate, and there's times when vector descriptions of something are more appropriate. Okay? It doesn't mean that scalar descriptions are any less accurate. Okay? A scalar description of something can be more accurate than a vector description. I just always get direction when I get a vector description. Okay, so if someone gives me a vector quantity, I get a value plus a direction. When I get a scalar value, I only get a value. Okay, so if somebody asks me, how far is it to Calgary, I can say 40 kilometers. And for most of us in this room, that'll be good enough. We know where Calgary is. Okay, we'll get on the road and go 40 kilometers towards Calgary and we'll get there. Okay, but if I'm talking to somebody who's from, I don't know, Hawaii, okay, they don't necessarily know where Calgary is. If I tell them it's 40 kilometers from here, will they get there? I mean, if they're reasonably intelligent, they'll probably figure it out by reading signs and stuff, but they would have 360 choices for what direction to go from here, 40 kilometers. Calgary's big enough and close enough that probably 50 of those would end up in Calgary, but okay, you get my point? Okay. Sometimes a vector description is okay, sometimes a scalar description is okay. Okay? For us in here, saying it's 40 kilometers from here is okay. We know where to go. Okay? If somebody's not from here, doesn't have a map, but a helicopter, for some reason they would have one and not the other, okay, they wouldn't be used. Okay? I need to give them a vector description instead. Okay. Everyone okay with that idea between scalar and vector? Okay, now a vector description would be more descriptive, not necessarily more accurate, but more descriptive. We'd say 40 kilometers away, 13 degrees west of north. Okay, that would get me downtown Calgary from here. Okay, that would be a vector description. Okay, not only tells us where Calgary is, but also what direction to go in order to get there by telling us what direction to head. Okay, now if I say 40 kilometers, it might be 40 kilometers, but is it possible I might travel several directions if I'm on the road? Is that possible? That's another reason why a scalar description doesn't always give a direction. Sometimes a scalar route involves actually going a lot of different ways. So you can't really give one direction, right? Because it would involve making a bunch of turns, right, as you go. All right, so now our vectors are not always measured in degrees. Okay, they will be a bit when we start getting into those kind of vectors. Sometimes they're just positive or negative, like you used in Science 10, right or left, up or down, okay, things like that. But we will get into the compass directions shortly. Now, if I say 13 degrees west of north, what does that look like? What direction is that? So if I draw why would I say 13 degrees west of north? Why wouldn't I just say northwest? Yeah, it's way more accurate. Okay? Northwest is like this whole sector. It's not nearly as accurate as saying 13 degrees west of north. Okay? That's a specific direction. Okay? And I need to be that specific. If I'm flying a plane, it's kind of important to follow that vector, or I'll miss the runway. Not bad. Okay? We'll kind of follow on that. Okay? So it's 13 degrees west of north. I don't just say 13 degrees northwest because that could be that way or that way. Okay? I said it's measured from north going west. So west of north. Everybody kind of follow on my direction finding there? Okay? You'll get used to that. It's probably new to you, but you'll get used to it as we go along. Okay, so let's just use this example. It's a simple example of the difference, or the way that scalar versus vector quantities would view the same trip. All right, so let's say I want to walk from my house to Walmart. Okay? Now, because I don't live right behind Walmart, I can't walk in a straight line from my house to Walmart because that would involve walking through walls, and yeah, I can't do that. Okay, so I get on the sidewalk, I follow the sidewalk, I take the bridge across the river, I follow the sidewalks and paths, and eventually I end up at Walmart. Okay, following this black path means I walk 4 kilometers. Okay, so I'm in black here. Okay. Is that my distance or my displacement? That's my distance. Okay, that's how far I had to walk to get from my house to Walmart. Okay, did I walk a number of different directions while doing that? Yes, I did. Okay, so it's a scalar quantity. I can't give a direction. It's just how far I had to walk. Is Walmart actually 4 kilometers from my house? No. Okay, but that's how far I had to walk to get there because there was no direct route. I don't have a helicopter. If I did, I wouldn't shop at Walmart. I could afford to shop elsewhere. Okay, I could afford a helicopter. Okay, so that said, when I get to Walmart, this purple line represents how far I have displaced myself from my starting position. Displacement is always that shortest straight line route between your initial position and your final position. Okay? So it's always going to be either shorter than your distance or equal to your distance. And it'll only be equal if you are actually able to do what? Walk on a straight line. Okay? That's the only time they'd be equal. Otherwise, distance will always be bigger. Displacement will always be smaller. Okay, so let's say that when I get here, I'm actually 2.8 kilometers from my house, 38 degrees north of west. Okay, so that's the magnitude and the direction. So Walmart would be 38 degrees north of west from my house, 2.8 kilometers. Okay, so that's my displacement. Everybody okay with those two measurements? Okay. That trip takes me a half an hour. How fast was I walking? Okay. How fast is speed? Speed is scalar. 8 kilometers per hour. Okay. How do we figure that out? Well, we understand that speed equals distance divided by time. The distance I traveled was 4.0 kilometers. It took me 1/2 of an hour. 4 divided by 1/2 is 8 kilometers per hour, which should make sense. If I walk 4 kilometers in half an hour, I'd walk 8 an hour. Everybody okay with that? Okay. What's my velocity? Velocity looks at this trip from a vector perspective. Close. It's not going to be 8 kilometers per hour though, right? Because my displacement is 5.6, right? Yeah, 5.6 kilometers. Okay, per hour. Okay, and what direction? 38 degrees north of west. Okay, here's why. Okay, velocity is my displacement divided by time. My displacement is 2.8 kilometers at 38 degrees north of west. That trip still takes me a half an hour. Okay? Still took me a half an hour to walk to Walmart. Okay? So when I divide 2.8 by 0.5, I'm going to get 5.6 kilometers per hour at 38 degrees north of west. The direction for my velocity is always going to be the same direction as my displacement. They are the same path, after all. Okay? It would be impossible for me to end up 10 kilometers north by walking 5 meters per second east. Agreed? Okay, so they'll always have the same vector. Okay, so that's stuff you would have done in Science 10. So is the next thing I'm going to ask you. I'm getting old, So I get to Walmart and I realize, oh crap, I forgot my wallet at home, which has never happened. Okay, but I get there and realize I don't have my wallet. Well, I mean, I don't like being in Walmart the best of the time. I'm certainly not just going to walk around in there for the hell of it. I didn't bring my wallet, so I had to turn around and walk home along exactly the same path at exactly the same speed. Okay, so I get home in another half an hour. How far have I gone? How far did I walk in total? 8 kilometers. Okay? My total distance that I walked is 8 kilometers. It was 4 kilometers to Walmart, 4 kilometers back. Okay? So it was a total of 8 kilometers. That took me 1 hour. What's my average speed? 8 kilometers per hour. 8 kilometers, 1 hour. Okay? Everybody okay with that? All right. I walked to Walmart. I walked home. I'm now back at home. What's my displacement? 0. Okay? Remember, displacement is final position minus initial position. My initial position was home. My final position is home. That's 0. Technically, I have not displaced myself from home. I'm back there. So my total displacement is 0. And what's my average velocity then? Also 0, right? Because velocity is displacement over time. And I just said my displacement is 0. So over the whole trip, even though I walked 8 kilometers in 1 hour, from a vector perspective, I accomplished nothing. Because I ended up back where I started. Okay? I got my steps in, but other than that, I didn't accomplish anything because I ended up back where I started. Okay? This is the exact reason why the odometer in your car measures distance. Okay? It would be useless for your car's odometer to tell you displacement. Because what would it always read when you get home?
0.
No, it would read how far it is from the dealership to your house. Nobody has ever gotten that question right when I ask it, by the way. Everyone just says 0. It's a knee-jerk reaction. Okay, but it would read how far it is from the dealership you bought it at to your house. Because every time you come back, that's how far from the dealership. True story. Every time you get an oil change, it'll read 0. Okay? All right. So, it would be useless then, obviously, for telling people how many kilometers are on your car. It'd be awesome, though, if you had this car that was like really old and like beat the crap out of it, but when they came to look at it, it said it had 3.5 kilometers on it. Okay? Which is exactly why it doesn't say that. Okay? All right. So, everyone following the difference there between a vector perspective and a scalar perspective on a trip? Okay. Here's another situation. So I'm on this trail here. I'm here at Seldom Inn Campground, and I want to go to Snake Indian Falls Campground. Okay? Just outside of Seldom Inn Campground, there's a sign that says Snake Indian Falls Campground, 31 kilometers. What is it telling me? It's telling me the distance to Snake Indian Falls Campground. Now, what is it assuming I'm going to do? Walk on the path, because that's what sane people do. Okay? You would follow this. If I go along this path, the distance traveled will be 31 kilometers. Okay? It does not have a sign that says Snake Indian Falls Campground, 24 kilometers at 41 degrees west of north. Okay? Because nobody would go this way. Okay? There's all manner of disaster here. Okay? There's like big waterfalls and deep canyons and glaciers with crevasses in them and stuff. People just wouldn't go that way. Okay? In that case, a scalar description is more appropriate than a vector one. Okay? If I'm a pilot and I'm flying from one island to another in an island chain, then a vector description is more. I don't have a path to follow. Okay? I need to fly in a straight line. Okay? So there's a time and a place for each. And we kind of have to understand when one is more appropriate than another. Okay, so speed and velocity, and this is a review from Science 10. Speed and velocity have this relationship. They both measure the rate at which you are moving. Okay, one from a scalar perspective, one from a vector perspective. Okay, your velocity, okay, measures it from a vector perspective. Distance and displacement have the same relationship. One tells you how far you've gone. The other tells you how far you've gone from your starting position in whatever direction. Okay? They're still looking at the same trip, but they're looking at them from different points of view. So as a result, they're calculated slightly different. Okay, so this terminology is hopefully a review for everybody, so I'm just going to go through it quickly. If I'm given a scalar quantity, that's a measured quantity that has only a value, 40 kilometers, 70 kilograms, 5 days, okay, something like that. Those are scalar quantities. Okay? Distance is a scalar quantity that measures how far an object has traveled. Speed's a scalar quantity that measures how far an object travels in a set time interval. So 20 meters per second, or 100 kilometers per hour, something like that. Okay? A vector quantity is a measured quantity that has both value and direction. 40 kilometers forward, 3.2 kilometers, 18 degrees west of south, 750 newtons down. Okay, that's force. Okay? Force is a vector quantity. Displacement is a vector quantity that measures how far and in what direction an object has traveled from its starting position. Okay, so there's direction and a reference point. That was not necessary here. Okay, for distance, it was just how far the object went. Okay, here it's how far, what direction from the starting position. Okay, velocity, vector quantity that measures the displacement of an object, again, during a set time interval. So same units as speed, meters per second, kilometers per hour. But tacked onto that will be whatever direction the object is going. Okay, our formulae. Okay, we're going to have speed equals distance over time. So v equals d over t. Okay, and velocity equals displacement over time. Still v equals d over t, but the v and the d both have arrows over top to denote that they are vector quantities. Okay? So those formulas should be familiar to you from science. Okay, questions on those? All right, so let's have a look at kind of a really simple kind of displacement type of question. Okay? So I've got this person who is initially 1.5 meters to the right of this Inukshuk. A little while later they move and they're now 3.5 meters to the left of the Inukshuk. Okay? I want to calculate their displacement. Okay? So displacement is my change in what? Position. Change in position, right? My distance from my starting position to my final position. Okay? Our formula for that is final position minus initial position. Now, I have left and right in this question. Those are opposites. How do I represent that mathematically? With a negative. Okay? So one of those directions needs to be negative, the other needs to be positive. Okay? So my initial position is 1.5 meters right. I'm going to make that positive. I'm going to make the left negative. So my final position is negative 3.5 meters. And I'm subtracting my initial position of positive 1.5 meters. Okay, so I started 1.5 meters right of this thing. I'm now 3.5 meters to the left of it. My total displacement is... Okay, so do I want to leave it as negative or do I want to represent it as it was represented to me? Is negative the same as left? It represents left, but is it the same as left? No. Okay, my final answer, I don't want to leave this as negative 5 meters. It's 5 meters left. Okay, that was my total displacement. I moved 5 meters to the left in going from my initial position to my final position. Okay. Questions on that one? I want you guys to try these 3 questions here. Okay? They're basically just like what we just did, but like some of them are easier. Okay? So don't overthink it. I'll give you a few minutes on those and then we'll walk through them together. Okay, so for number 3, okay, we've got this person building a brick wall. Okay, so they're moving the cement back and forth. Okay, she moves her hand back and forth 1.70 meters 4 times. So she goes 1.70 meters out, and then back, out, and then back. What's her total displacement? 0. She ended up back where she started. What's her total distance? Yeah, 1.7 times 4, right? Would be the total distance to travel, okay, and going out and back 4 times. Okay? All right? Everybody okay with those? Pretty straightforward? All right. Okay, I want you guys to see if you can draw the seating plan that they're talking about in question number 4. Okay, so I want you to put these people like they're on in a row. Okay, and I want you to put them in the right order. Right? All they tell us is Chad's 2 meters left of Dolores, Ed's 4.5 meters right of Chad, Greg is 7.5 meters left of Chad, and Hannah's 1 meter right of Ed. Okay? So I want you to draw that seating plan and then calculate the displacement of a teacher who walks from Greg to Hannah. There's something this question's trying to illustrate. I'm going to point it out to you after you've had a little while to think it over. Try number 5 here. A person's displacement is 50 kilometers west. Okay? I want to know their final position if they started at 5 kilometers east. Okay? The tip I will give you is this. Displacement is final position minus initial position. Give you a minute. Okay, so this should be a fairly quick one. Did they give me 2 out of the 3 parts of this equation? Yeah, they gave me the initial position, they gave me the displacement. All I have to do is manipulate to find my final position. Okay? So if I'm going to get final position by itself, what do I do with initial position? Add it over to the other side, right? Okay, remember, 3 rules to algebra. If I want to move something, I do the opposite. What I do to one side, I do to the other. And I move what's not attached to what I'm looking for first. Those are the 3 rules of algebra. You'll need those 3 rules, okay, in this course. All right, so I'm going to have displacement plus initial position equals final position, okay? But I've got east and west, so I'm going to make west negative, and I'm going to say negative 50 meters, okay, plus 5 meters, okay? The 5 being east being positive, right? Which means that my final position is negative 45 meters, which is 45 meters west. Okay? That should make sense. If I started 5, sorry, is it kilometers? Sorry, it's kilometers. I wrote meters. Okay, so if I started 5 kilometers east of something and then moved 50 kilometers west, I should now be 45 kilometers west of that something. Agreed? All right, see if you can apply that to question number 6. Okay, so you got these 2 people playing with an otter, which is a sealskin racket, apparently. So, standing 3 meters apart, the child on the right tosses the ball to the child on the left. Okay, so where does the ball start?
0. That's all 3 meters.
Okay, who has it, the purple or the green?
Green.
Okay, it says that the person tosses the ball to the child on the left. So that means that the ball starts here, because this has to be thrown 3 meters to the left. Everybody with me? Okay, so they throw it 3 meters left. Then this person runs 5 meters this way to catch the ball. How far did the ball travel? Knee-jerk reaction, 8 meters. What's the actual distance it travels? The ball goes from here to here and then to here. That's 11 meters. Okay? We always have to watch our knee-jerk reactions. They're often wrong because they just look at the numbers and forget that it actually traveled that 3-meter distance twice. Okay? Now, what's the displacement of the ball? Five meters. The ball started here. The ball ends up over here. The ball's displacement is 5 meters to the right. Okay? Lots of times the simplest questions can be very misleading if we're not careful about reading them carefully. Okay? All right. Now, advice. Let's do this. Okay, B equals D over D. Should be a fairly straightforward formula to manipulate. I'm going to be brutally honest with you. If you just did this, or were thinking of doing this, you should drop this class. Okay? I'm just being brutally honest. Okay? If that's how you do algebra and manipulate equations, that's very bad. Okay? Because next week, we'll do this formula. There's no triangle for that. There's no rhombus or octagon or anything that will work to help you manipulate that equation. Only the 3 rules of algebra will help you manipulate that equation, similar to this one. Which we will use later in this course, or this one. There's no triangle for that one either, okay? And I'm just being brutally honest with you because I don't want you to waste your time, okay? If algebra is something that really gives you trouble, this course is full of it. I mean algebra, full of algebra, okay? So just be aware of that, okay? There's a lot of math and a lot of algebra in this course. If that is something that really frightens you, this might not be the right place, okay? So if I'm going to manipulate v equals d over t, okay, let's say I want to manipulate for d. What do I do with t? Just multiply it over to the other side, right? Okay, like so. All right. What if I want to solve for t? Right. Multiply t over and then divide by v. Okay. Just have to remember the 3 rules of algebra. Okay, now the 3rd rule obviously doesn't apply to this formula, but it would apply to one like this that you would have used last year. Y equals mx plus b. Okay, if I want to manipulate that, what should I move first if I'm solving for m? I should move b, because b is not attached to m. Okay, that's where the 3rd rule comes in. How do I move b? Okay, so y minus b equals m times x. Now what do I do? Divide by x. Okay. Okay. If that's not giving you any trouble, you're good. Okay. You can do algebra, no problem. Okay. This is the right place for it. Okay. If what I just did there looked like Greek. Okay. All right. Here's a question you would have got in Science 10. Okay. It's a v equals d over t question involving more than one part to a trip. Okay. It wants to know both the average velocity and the average speed of the garbage truck. So, little tip. This formula that we always use actually means this. Average equals total over total. Okay? So if I'm talking about average speed, it's total distance over the whole trip divided by the total time over the whole trip. Okay? And it's the same for velocity. It's the total displacement over the whole trip divided by the total time of the whole trip. So, see how many of you can get that. Okay, so the reason I wrote these 2 formulas up here is because there's a knee-jerk reaction that usually happens with a question like this. Whenever someone hears average, they go, add together, divide by the number I added together. Okay, so people tend to do this. They take the 4 meters per second, they add the 16 meters per second, and then they divide by 2. Why does that not give you the average velocity for this trip? Okay, it doesn't account for displacement, and it doesn't account for the fact that the bus only went this fast for an incredibly short period of time. This doesn't account for the same amount of the trip as this does. The bus moved at this speed for like 85 or 90% of the trip. Okay? Where it only went 10% of the trip here.
Everyone.
Okay? We'll talk about the rest of that one tomorrow.
Our closing